Okay, so I will welcome Dr. Pankaj Sarkar to our 6 days online FDP on RF energy harvesting.
Thank
So
you.
now at first I would like to introduce Dr. Pankaj Sarkar. Dr. Pankaj Sarkar presently working as an assistant professor in Electronics and Communication Engineering Department of Northeastern Hill University, Shillong. He has more than 70 publications in various national or international journals and conferences. He is the reviewer of various reputed journals. His research interest lies in the area of microwave active and passive circuit design, application-specific integrated circuit design, and the development of reconfigurable antennas. Currently, he is working to develop various agroelectronics products under CHIPS to Startup program of METI, Government of India. He has organized various workshops and international conferences in his capacity. So now I will request Dr. Pankaj Sarkar to start his presentation. Thank you.
Thank you, sir, for your brief introduction. So the topic already you have seen that I'll be discussing on the reconfigurable filtering antenna. So enabling multi-functionality in wireless system. Can you hear my voice properly? Hello, am I audible?
Yes, sir.
Okay. So this is the outline of my discussion. That's introduction. I'll about the reconfigurable filtering antenna, then applications. So I'll be discussing different types of reconfigurable filtering antenna. Then I'll be focused on how a dual band reconfigurable filtering antenna can be developed. I'll move towards again triple band reconfigurable filtering antenna. Finally, we have little conclusion and references. And in between also, if you have any queries or questions, that also you can ask. So introduction. So reconfigurable filtering antenna. Okay. So the antenna and the filtering. See, this part is filtering antenna. What exactly that means? Okay. So we are basically combining the characteristics of filter and antenna together. Okay, right? Because in every RF front end or the receiver end, we have filter and antenna, right? So filter and antenna, we are cascading together. Okay, and along with that, some sort of extra functionality we are going to introduce in a reconfigured filtering antenna. So what we are going to do here, we are basically going to develop the reconfigurable filter plus antenna characteristics, right? Okay. The filter which can be reconfigured. Okay, we'll see more in detail. Okay. So what is the advantage? The major advantage that is that it has the ability to adapt to varying operational requirements, right? Okay. As per the requirements, okay, you can change its characteristics. Okay. So in terms of operating frequency or maybe the polarizations, okay, or maybe the bandwidth, whatever. So as per requirement, you can change its characteristics. Okay, so that is what is called reconfigure. Okay, you can reconfigure. So as if we look at the how it is working, okay, so let's look at the spectrum which are available to us, known spectrum maybe below 10 gigahertz. Okay, so we have very limited unlicensed band, right? Okay, most of the bands are lower frequency bands are occupied. Okay, so these are various frequency and the corresponding technologies, okay, which are dedicated to this frequency, right? We have 2G, 3G, LTE, then we have Bluetooth, WiMAX is there, then Wi-Fi frequencies are there from 5.1 to 5.9 gigahertz. Bluetooth is operating 2.4 to 2.5, then 5G 3.3 to 5 gigahertz. LTE is there, okay. WiMAX is there at 3.2. So these are the various brands which are already licensed. They got the license to do the transmission and reception. So our target is that a single system we are trying to develop, okay, and that system can this be utilized for transmit and receive signals for all the applications. Okay, means a system can this be developed which can be used as a Wi-Fi transceiver system, or if required, the same system. Okay, the same system I'll reconfigure such that it will act as a WiMAX device. Okay, it will act as an Bluetooth device. Okay, I'm not going to change the devices. Only I have to reconfigure the system. Okay, means if we can do that, means no need to carry or no need to procure multiple devices for all these operations. So that is what our target is. Okay. If you look at a very simple transmitter, so transmitter is consisting of, hello, this transmitter basically consisting of this minimum number of block diagrams, which I have illustrated here. So we have a processor unit, then DAC we have, then bandpass filter, then mixer. In mixer, we are basically getting the digital signal modulated with some carrier, maybe the intermediate frequency. Here I have considered two cases. Okay. So one case, suppose this entire system is operating to transmit and receive the signal for Bluetooth. So processor will do some processing, that data we have to transmit. It will come to DAC, and bandpass filter will be used to pass this particular carrier of 1 gigahertz. Then in the mixer, we are going to mix the signal along with the local oscillator signal. Because as we are going to use this device or this transmitter as a Bluetooth transmitter, so what will be the radiating frequency? The radiating frequency will be 2.4 gigahertz, right? But the frequency which is carrier frequency is coming from the processor, okay, that is coming say 1 gigahertz. So I have to do the up conversion. So for that, 1 gigahertz will be mixed with 1.4. Then I'll be getting two different bands. Upper sideband will be 2.4. So and from 2.4 signal will be passed through the power amplifier. It will feed it to a bandpass filter which is operating at 2.4. And finally, that signal will be fed to antenna, and antenna will radiate the data with a carrier frequency of 2.4, right? Okay, this is what we have, a very typical transmitter. Now, the same transmitter, if I want to use for WiMAX, say, WiMAX is operating at 3.2, means WiMAX will send the data with a carrier frequency, or sorry, with the RF frequency of 3.2 gigahertz. Now, can this same system be utilized to transmit the WiMAX? Yes, we can do that. The processor part, you can program it according to that. You'll be getting the desired data. And at the mixer part, as it is providing you the same processor, so it is higher frequency will be 1 gigahertz, again the same like Bluetooth. But as I am to transmit the 3.2, so the local oscillator frequency I have to change. So I am changing it to 2.2 gigahertz instead of 1.4. Now I'll take 2.2. Now, after mixing, I'll be getting 3.2 gigahertz, right? Okay, so 2.2 plus 1. So upper sideband I'm considering, so 3.2. So 3.2 gigahertz signal will pass to the power amplifier. It will come to the bandpass filter, which is operating at 3.2. And after that, this signal will be feeding it to antenna, and antenna will radiate, right? Okay. So the system can be means reconfigured. So it can be configured from Bluetooth to WiMAX. The same way the reverse thing can be done. So what I supposed to do? So if you look at this part, okay, so this particular part where the processing we are doing, where we are basically doing the data processing, that part is not required to change. Okay, so only this particular bandpass filter and the transmitting antenna, this I have to change, because the bandpass filter initially for Bluetooth it was operating at 2.4, and antenna was also operating at 2.4. Now, as you are moving it to WiMAX, so operating frequency, it will not be 2.4, it will be 3.2. So the center frequency of the bandpass filter has to change from 2.4 to 3.2. Similarly, the antenna should operate not on 2.4, it will be operating at 3.2 now. Okay. So what is required to change? We required to change the bandpass filter and the transmitter part. Other part you can keep as it is. And additionally, you need to change the local oscillator frequency. See, initially for Bluetooth, the yellow frequency was 1.4. Now I have 2.2. So I can design a voltage control oscillator where the external voltage can be applied to the local oscillator to change its local oscillator or the resonance frequency. So with the help of voltage control oscillator, this entire system can be reconfigured from Bluetooth to WiMAX, or again the WiMAX to Bluetooth. This can be done. So my discussion will be focused towards this particular part. Okay. So band pass filter plus antenna, how this entire part can be reconfigured based on your requirement. Is this clear? So what is the So what is the advantage? Advantage is that this enable multi-band operation. Okay, because the modern communication devices I have mentioned earlier, they need to operate in multiple frequency bands. So reconfigurable filtering antenna can switch without need of multiple antennas and saving the space requirement and reducing the complexity. Right? As I have mentioned that we don't need to go for multiple antennas or multiple band pass filter. Okay, that because the remaining part of the transmitter is similar. So this
Not audible.
No, yeah, it is not audible.
Sir, not audible.
Yeah, yeah. Please wait. Please wait. Actually, I think that
Only one,
there will
sir.
be some issue. Yeah,
Sir, just kindly clarify one thing. Sir,
yeah,
every day, whatever presentations will be there,
yeah.
at the end of the day, the presentation will be shared or not? Means through some
No, it is
email
not
or.
at the end of the day. It is not at the end of the day. Actually, I'm not getting all the presentation files at the end of the day itself. So
Okay.
all the files will be sent after completion of the FDP. You will get everything.
Sir, then how to prepare for this test, sir? At the end of the FDP, there will be one test, na?
Yeah, one test will be there, but for that test, the concerned material will be uploaded in the Auto website. You can check your website. Already one material I have uploaded. Related material
Okay,
will be
okay, okay,
uploaded. Related journal paper is
okay,
already uploaded in the Auto, by which we can prepare yourself for the test. Okay.
okay, 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 okay. Thank you, sir.
Okay. 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 So, dear participants, actually some technical issue is going on with the speaker. So I think that's some kind of power failure maybe there on his side. So you are requesting all of you, I am requesting all of you to wait for 5 minutes at least. Thank you.
Can you hear me? Can you hear my voice?
Sir, you are audible. You can go ahead.
Okay.
Yes.
There is a sudden power failure here.
Yeah.
So which was the last slide actually? I forget that. I was here
Go
or
back,
what?
go back, go back, go back, go back, go back. Yeah.
No,
Yeah. No, no, no,
this,
no. Next, next, next. Next slide. Next slide. Just go to next slide.
this one?
Back. Yeah, that one. Start.
Okay, thank you, thank you. Okay. So these are the different types of reconfigure filtering antenna. So we have reconfigure filtering antenna, which can switch from one frequency to another frequency. That is called frequency reconfigurable, right? The first case, which you can see here. Okay. So the operating frequency I can change from 1 to 2, 2 to 3. This is how it can switch, right? Okay. Then the radiation pattern can also be reconfigured. Okay. So you can generate various pattern, okay, by reconfiguring the filtering antenna. Right. Then polarization reconfiguration is also possible. Okay, means you can switch the antenna from linear polarization to circular polarization as per the requirement. And one we have the hybrid is a combination of these multiple characteristics of frequency to polarization combination or radiation pattern frequency combinations. Okay, so this is how a hybrid reconfigurable filtering antenna you can design. So my prime focus will be on this particular part, how the radiating frequency can be switched from one frequency to another frequency. So this is how I'll do. So I'll look for a device. Okay, so I'll look for a reconfigurable filtering antenna or wireless technology which can switch from Bluetooth to LTE or Wi-Fi or 5G or GPS. Okay, the operating frequency I need to switch from one band to another band. So what are the main electronic switches which are basically used to switch the operating frequencies? We can use MEMS, we can use the pin diode, we can use the varactor diode. Okay, so these are some electronic devices which we should use for designing your filter and antenna to switch the operating frequency to multi-bands. So here you can see a simple structure which will help you to understand that what is the basic need. See here, the reconfigurable filter, what we will do. So suppose we have multiple antennas. Okay, so this will be normal filter and antennas. Okay, so this antenna may be operating at 2.4, another is operating 3.2, and last antenna is operating 5.5. So if you want to generate a system which will operate in multiple frequencies, then you need to have multiple antennas along with the filter. But in reconfigurable filtering antenna, only one antenna or only one multiband antenna or broadband antenna you can use instead of using multiple antennas here, which we have used here. Instead of using multiple antenna, you can use a single antenna. It can be broadband or multiband. Okay, So the reconfigure filtering and the filter will decide that which frequency the antenna should radiate. Okay, so you can switch the operating frequency from one to another. Okay, and antenna will start radiation. So for that case, the end antenna must be multi-band or broadband. Okay. So reconfigurable filter, we have two basic reconfigurable filter. One is the continuous tuning, another is discrete tuning. Okay. So continuous tuning means what? The operating frequency will be tuned continuously. See here the first case. Okay. So here the continuous tuning. Continuous tuning, what is the characteristic? See the S11. S11, how it is the varactor diode, external voltage you have to apply to the varactor, then the operating frequency is continuously switching. See, it was initially say at 0.8, then it will move 0.8 to 0.81, 0.82, 0.83, this way it will go up to say 1.1. Okay, this is a continuous tuning. This is not discrete tuning. So continuous tuning, we are basically design using varactor diode. Okay, so the electronic devices, varactor diode basically used to develop a reconfigurable filter which can achieve a continuous tuning. And if you need discrete tuning, am I audible?
Yes, you are audible.
Okay.
Please go ahead.
Discrete tuning.
Yes, yes.
Discrete tuning, we are basically designing using pin diode, okay, or MEMS switch. Okay. So discrete tuning is what is the characteristic? See here, you can see here we have a filter which is dual band in nature. We have two different bands, which is basically.
Pankaj sir, you can off your camera. No problem. Actually,
Okay.
it is not visible. You can off.
Okay. Okay. So switching here, you can see we have designed a dual band filter, reconfigurable filter, where as per your requirement, you can switch. Say dual band can be switched to a single band. See, initially the band was centered at 3.25 and another band was at 5.35. Okay. So if you want to switch on one band, that is possible. See here, the second case, the same filter, reconfigure filter, the one band, the second band we have switched off. Here it is behaving like a single band pass filter. Okay. Then the third case. In third case, what we have done, we have switched off the first pass band. We have only the second pass band. Okay. So first pass band is switch off, second pass band is working. Okay. And the fourth case where both the pass bands are not working, right? Okay. So how can you reconfigure? You can reconfigure from dual band to single band, again to another single band, and also you can have a all stop operation. Okay, so this kind of switching is possible. So this we are developed using pin diodes. Okay, this is more fruitful because if you look at the practical applications, there you need discrete tuning compared to a continuous tuning. Continuous tuning will move through different bands. Okay, but in discrete tuning, there's two targeted bands which you are looking into, so that can be reconfigured as per the requirement. Okay. So I'll discuss few of reconfigurable filtering antenna, how the reconfiguration can be done. Okay, so as I had mentioned earlier, that I'll go for a dual band reconfigurable filtering antenna using pin diodes for WiMAX and WLAN applications. Okay, so then I'll move to triple band. Okay. So in dual band filtering antenna, we are going to develop here, which will be my target band is WiMAX and WLAN. Okay. So WiMAX means 3.2 gigahertz and WLAN we have 5.35 because WLAN there we have three consecutive bands. Okay, but I'm looking for the mid band only 5.35 gigahertz. Right. And the pin diode we are using for switching elements. Here you can look at this part I already have mentioned. So still you can look at the different bands which are below 10.6 gigahertz. Okay. So I have to design and both I'll cascade together and to develop the reconfigurable filtering. Okay. So reconfigurable filter design. Okay. First I'll discuss the filter part, then antenna, then after combining these two, how the response look like, that part I'll discuss. Okay. So reconfigure filter, first we have to develop this filter using resonators. Okay, you know that resonator are basically used to means varieties of resonator I can use to develop the filter. So here I have used step impedance resonators. Okay, so what is the configuration of dual band filter? So means I'll be getting dual two different passband. The way I have, you can see here, I'll be getting two different passband, 3.25 and 5.35. So 3.25 I have for to develop or to generate the passband at 3.25. What I have done between your source to load, between your input and output. Okay. So I have used one
Excuse me,
resonator.
sir.
Yes.
Sir, just for interrupting, what is the bandwidth, sir, of these two bands? If you highlight bandwidth,
So
fractional
bandwidth,
bandwidth.
okay, you'll get to know. Don't worry. One is 5.7% and fractional bandwidth, and 6.3. Another is 5.3.
Okay, sir. Okay, because I am noting down this. Okay, thank you, sir.
Okay. So while designing this fractional bandwidth is the initial step that whether we will really achieve that amount of fractional bandwidth or not. Okay. So let's see the structure first. Then we'll go for the bandwidth part, how the required bandwidth can be achieved. Okay. So I'll discuss more detail about this first structure such that the entire steps of design process you can understand. Later on,
Sorry to disturb. Your PPT is not visible. Sorry to interrupt, but
is this for all or only for you?
all persons,
All participants.
all participants.
Mr. Pankaj, you can check that your PPT slide is not visible.
Sir, at my side, actually, I can see reconfigurable filter slide. It is visible
Yeah.
from my side.
No, I can also see. So I'm in the same slide only, the reconfigurable filter design.
Yes, sir.
Yeah.
That I can see.
Okay, maybe problem with the other participant.
But we can't see.
Ma'am, please tell me.
We can't see.
Sir, we also can't see. Sir, I can't also see.
Because many participants, few are telling they can see, but from my side there is no
Yeah.
network issue.
It is not visible. Actually, it is saying something annotating or something. It is
Yeah,
saying.
Pankaj is presenting, annotating. Yeah.
Pankaj, you can whatever. I think that my
Can you see
suggestion
that I'm changing the slides? Can you see this?
slide is not changing.
No,
No,
slide
is
is not changing. It is
No, we
showing
can't see.
reconfigurable filter only. That slide.
Slide is not changing. So, Mr. Pankaj, I will suggest that you kindly stop your presentation and again restart your presentation.
No, but if slide is not changing, then just a minute.
No. So, it is better to stop presentation from your side and then restart your presentation.
I'll do that. I'll do that.
Yeah.
That will be better. Okay.
Is it okay now?
Yeah.
Yes, sir.
Yes, sir. Now it is visible.
Yes, sir. Yes, sir.
I'll turn off this video. Okay. Is this okay? And I'm changing the slide. Tell me, please.
Yes, sir. Yes, sir.
Yes, sir.
Okay, changing. Okay. I
Okay,
was in this
okay.
slide. Will I continue with this or? Can you hear me?
Next slide. Please go to next slide.
Yes, yes.
This one.
Yeah.
Okay.
Yeah.
Right.
Okay.
Thank you.
You can restart that.
Because there is a power failure. So anything, any moment, anything may happen. Please let me know. Okay. So what happened here that we are basically developing two dual band filter, so which has a pass band at 3.25 and 5.35, right? Now how I'm doing that, see here. So I'm constituting two paths. One path, resonator 1, resonator 3, and resonator 2. This is used, okay, to develop a pass band at 3.25. Okay, clear? So the signal which will pass through the resonator with a frequency of 3.25, it will go from resonator 1 to 3, again 3 to 2, and it will come to the load. So this is one path, and through this path, who will pass through 3.25 gigahertz. And the lower one I have designed to pass or to generate the pass band at 5.35. So 5.35, it will go from resonator 1 to resonator 4 and resonator 2. Okay. So resonator 1 is holding both the frequencies, F01 and F02. Means F01 means first pass band frequency as well as the second pass band frequency. Similarly, the resonator 2 also holding both the resonating frequencies, okay, 3.25 and 5.35. Now the upper one, the resonator 3, is basically designed to resonate at 3.25 only, and this one is designed, this lower one is designed to resonate at 5.35, right? Okay, this is how you can say the coupling scheme look like. Okay, this is how the dual band filter is designed, right? Now this resonator, because see 3.25 and 5.35, single resonator, if it is resonating, it can resonate in multiple frequencies, right? But their order will be n into lambda by 2. Okay, but here you see 3.25, the second one supposed to be 6.5, but instead of that I'm using 5.35. Okay, so some simple resonator will not resonate at this fractional order of frequencies, right? This relation is not integer, it's a fractional. So for that purpose, what we are doing, we are using SIR. Okay, resonator 1 and resonator 2, we are basically using step impedance resonator. Okay, so where the here you can see here. So this is your step impedance resonator. In step impedance resonator, what is the characteristics? The impedance, or I can say that if you look at the entire length of the resonator, which is open end, so this end is open, this end is also open, but their widths are different. See here, this is narrow width, and this part of the resonator is wider in width. Okay, that's why it's called step. There is a step in impedance. So narrow width is basically telling you the high impedance sections. This is your low impedance section. So both the entire section of your resonator is not uniform in width. Okay, so with that you can develop a harmonics which will be in fractional in order. Okay, relation between them will be different, not in integer order. Right? So here we are using SIR with an impedance ratio of 2.25. The higher impedance section we are considering 112 ohm, and low impedance section we are taking 50 ohm. So resonator 3, this resonator 3 is also designed using UIR. The fundamental step impedance resonator fundamental frequency of 3.25, and the bottom one is generating the second pass band. So the fundamental frequency of resonator 4 we are considering at 5.35. So this is how this entire filter look like, right? So this first resonator, the first resonator is basically resonating at 3.25 and 5.35. This is at 3.25, and this is again 3.25. Okay, so signal will pass through 3.25, and this one is resonating at 5.35. So this three resonator will give you 5.35, the bottom side. Okay, now you'll be getting two pass band for this. Okay, now when you'll be designing the filters, okay, the crucial point is that what should be the fractional bandwidth, means what will be the bandwidth. Some of the participant has mentioned earlier that what should be the bandwidth of the filter. Okay, so from the bandwidth you have to see. So these are the resonance which I have mentioned. Okay, so see here. Okay, so bandwidth we are considering for first pass band we are considering 6.3% fractional bandwidth. Okay, and fractional bandwidth for second passband we are considering 5.3. This is as per the specification of the bands. Okay. Now, to achieve the desired bands, okay, what should be the external coupling and the mutual coupling between the resonators? That you have to find out, right? Okay. So see here, how much bandwidth individual band will achieve. Try to understand this part. How much bandwidth the individual band 3.25 and 5.35 will achieve 6.3 and 5.7 something. So that is fully depends on what these feeding positions. So see, this is my feeding position, right? That port 1, this is my input, and here from I'm extracting the output, right? So where it will feed means this length L2. So the location, you see, this feeding line you can place here also at the middle of the SIR or at the top of the SIR you can place. Okay. So similarly, output side also anywhere you can place, but your bandwidth will change. Okay. So your bandwidth will tell you that what will be the value of L2, means what is the feeding positions. Not only that, the mutual coupling between the resonators. Okay, see here. So resonator, the EM signals will couple from this particular resonator to SIR3, right? So if you look at the first band, 3.25, how the signal will be coupled? It will be coupled from SIR1 to SIR3. So for that coupling, who is playing role? This particular length L7. See here. Okay. So L7 playing a crucial role. See here. The L7 is playing a crucial role as well as the gap between the resonators. Okay. So gap, if you are fixing, suppose I'm fixing the gap, then the entire control, okay, of the mutual coupling is coming in the hand of L7. So if L7 is more, if L7 length is more, means the SIR3 will be penetrating more inside this gap, right? It will be going inside. Then coupling will also be more because L7 is increasing. If L7 is reducing, means coupling will also be reduced, right? So L7 is playing a crucial role to get or to achieve the desired mutual coupling. Mutual coupling means coupling between the consecutive resonators, right? The same way, if you look at the second band also the L8 is the deciding factor of the mutual coupling, right? So for your bandpass filter to achieve the desired bandwidth, you need to control the feeding positions, means you have to find out the L2 as well as the L7. Okay. Is it visible?
Yeah.
Okay. Now see here. So this is some resonance characteristics of the SIR1 and 2, SIR3 and 4. Okay. So let's see how they really look. This I have extracted using the weak coupling. SIR1 and 2, solid line. Solid line, if you look at solid line, I have one resonance at 3.2. See, around 3.25, I have one resonance. I have one resonance at 5.35. I have another resonance at 6.5. Similarly, multiple resonances are coming. Now you see here, a simple SIR1 and 2 is resonating in multiple frequencies. Means I supposed to get multiple bands. My target is to generate dual band, not multi-band. Means here I can see 5 bands, which is means up to 14 gigahertz. Okay, but I'll be focusing only on 2 bands, right? That is the reason that I should avoid of generating multiple bands. How can I do that? So this band will also be generated, but I should avoid to generate a passband centered at 7 gigahertz, right? I should also try to avoid generate a passband at 10 gigahertz. How can I do that? So that will be controlled by the mid resonators. So these mid resonators you have to design such a way that higher order harmonics should not couple through the SIR3. Is this clear? Right? See here, the SIR1 will contain multiple frequencies. So what are the frequencies? 3.2, then 3.2, then 5.2, then we have at 7, we have at 10. Okay. But when I'll get a passband, I should get passband only for 2. Remaining 2 frequencies should not pass through this resonator. Means I should generate a resonator SIR3 such a way that it should couple only 3.25, not the other frequencies. Same thing is valid for SIR4. SIR4 I have to design such a way that from the SIR1 it should couple only 5.35, not the other frequencies. Okay, is this clear? Now for that, what we are doing, the SIR3 I have designed such a way, see here the dotted line. Okay, I designed such a way that, see, the first fundamental is coming at 3.25, but if you look at the second harmonic, first harmonics is coming at 8, which is not overlapping with any other resonance of the first and second. Understood the trick? Okay, so I have designed the SIR3 such a way that it should not couple, see, it's not merged with any other frequencies of SIR1 and 2. Means, as it is not part, there is no common frequency. So only one common frequency is 3.2. So 3.2 will pass through. Similarly, SIR4 I have designed such that it has a fundamental resonance at 5.5 gigahertz, and second resonance is coming at a frequency where it will not merge. Okay, so only one passband I'll get 5.35 out of this SIR4, and other band will not appear. Okay, so from this diagram I can easily understand that I'll be getting only two bands. One is this one, and another is this one, and other bands are fully decoupled. One is not coupling with the other. Okay, so this is how the upper or higher order harmonics I am suppressing. Okay, so this is the coupling scheme, the first band and second band. Okay, and this is how the external coupling and the mutual coupling coefficient I have to calculate based on the fractional bandwidth. So when you are designing the filter, you have to see that what kind of filter you are going to design. It will be third order, right? Because between your source to load. Okay, so between your source to load, between your input and output port, how many resonators are coming into picture? 3. So first, second, and 3. So order will be 3. Here also 1, 2, 3. Although I am using 4 resonators, but between your source to load, for a single pass band, it will encounter only 3 resonators. So order is simply 3. Okay. So for 3.25 also it will be ordered third. For 5.35 also it will be ordered 3. Okay. So order is 3. So you have to choose what kind of low pass prototype element you have to utilize for designing a band pass filter. I have considered Chebyshev low pass filter. You can get the element values of Chebyshev low pass filter. Okay, for third order low pass filter. And from there you have to calculate the external coupling. Okay, and the mutual coupling coefficient. Right. Okay. So we are calculating the values of mutual coupling coefficient. Okay. So 0.57 and 9 for first pass band, and 0.487 is for the second pass band. The external quality factor is coming 16, and for the first pass band, and the second pass band is showing 19. Okay. And this is how the L7 is L2. See here. This graph will tell you that what will be the value of your L2 to achieve the desired coupling. See here. So we have 16. 16 will come somewhere over here. 16. Okay. 16 will come to 16. Okay. So 16. Blue one is for the second. Second is 19. 19 means close to 20. Suppose this is the 20. 20 will come to this particular point. Below that, we have the first pass band, which is basically 16.37. So for this particular point, so what is the corresponding value of L2 will come, that you have to see. Okay. So L2 will come, say, around 4.5, 4.7 like that. It will come 4.5 and 4.75. So 4.7 to get the external coupling of 16.37 and 19.46. Similarly, the mutual coupling also will tell you that how much will be the L7. Okay, you have already calculated the mutual coupling coefficient for first and the second pass band based on this data, 0.0579. So here somewhere over here I'll get the value. So you'll get the desired length of L7. So L7 may come around 8.6. Okay, to get the desired coupling coefficient for second pass band. It was 0.487, so it's showing 3.5. Okay, so this is how the L2 and the L7 and L8 data will get. Okay, so once you place this, Okay. And one more thing, as so this part I'll come later. So once you will get this, you will be getting these two pass bands, right? See here, two pass bands we are getting. And along with that, you can see we are getting multiple transmission zeros. Okay. So multiple transmission zeros, we are getting basically this structure. Okay. See here. So here we are basically generating two paths, right? From your input to output. Okay. From input to output, we have two paths. So path one is going from resonator one to top resonator to this one. And another path is through the bottom resonator. Now, the signal can pass through from port 1 to 2 to through different paths, these two different paths. Now, the signal which will pass through top resonator, and the signal which will pass through the bottom resonator, if it is coming at port 2 with out of phase, those signal will be cancelled out fully. And for those signal, we'll be getting transmission zeros, right? So here we have find out the resonating the frequency of transmission zeros. Okay. For ABCD matrix, we have determined the S21 parameter. We have mentioned S21 parameter 0. And for zero condition, we have got several transmission zero equations. Okay. And based on the value of L1 and L2, the length between your input and output port. Okay. So we are getting zeros at 2.6 gigahertz, 3.95 gigahertz, 5 gigahertz, and 6.3 gigahertz, right? So here you can see that multiple zeros we are getting because of this multi-path propagations. Okay. So it will help to improve the selectivity. You can see that it's very highly selective passbands we are getting because of this transmission zero. And out of band attenuation is very high. So you see here, if you look at the out of band, we are getting close to 30 dB attenuation. And passband S21 is also quite good. Okay. Now, this is a simple multiband, but I am to make it reconfigurable. How can I do the reconfigurable? See here, I have used the pin diode. So resonator one edge I have connected pin diode, and cathode I have connected to ground, right? Similarly, this resonator 4, I have connected one pin diode and cathode I made it ground. And this pin diode I have biased through a RFC using some VDC. Okay. So when this particular diode will be forward biased, I have to use, see, when you cannot directly give the VDC to the pin diode, okay, or bias voltage you cannot apply directly to the pin diode, because see here, the signal can pass through this particular path. Can you hear me?
Yeah, you are audible.
Okay, thank you. Now the signal, when it will be traveling from port 1 to 2, where the signal will come to resonator 3, then it may get a path, right? If you are not using RFC, then through this path it may leak. Then there will be a huge attenuation at the output. That signal will be attenuated. S21 will not be close to 0. It will be huge attenuation we will be getting. So to avoid this leakage through this VDC wire, I am using one RFC, radio frequency coil you have to use. It has a certain inductance, maybe in between the range of 2 to 3 nanohenry. Okay, so we are using this amount of inductor here. And as I'm placing the inductors, obviously the RF signal will be blocked by the inductor. So RF will not leak through this particular path, so it will go to the output end. Okay. So to stop the RF leakage, always you have to provide this RFC. Now, once the VDC will obviously pass through, inductor will not oppose. So once the VDC you are applying, if it is forward biased, then the equivalent circuit of the pin diode will look like this. Okay, means this particular diode will offer you a very low inductance with a very low resistance of 5.2. Okay, so this particular diode will offer you very low resistance, means I can say that, okay, so this particular end of the SR will be connected to ground. Okay, when it will forward biased, this path will offer a very low resistance. So this edge of the SR will be directly connected to the ground. As it is connected to the ground, obviously the resonance behavior of the SR3 will be different now. Means, see, initially it was open-ended. When we have designed this, see here, when it was resonating, it was open-ended. But now if I'm connecting a ground at the edge, the resonance behavior of the SR3 will change. This SR3 resonance behavior will change. It will not resonate 3.2. If it is not resonating at 3.2, so there will be no coupling of 3.2 gigahertz signal from SR1 to 3. The signal will not pass to 2. Means once the VDC you are applying to diode 1, your first pass band will be blocked. Okay, it will not appear. Okay. Similarly, when you are applying, if you are not providing any kind of DC voltage, then if you are not providing any kind of DC, then what will be the equivalent circuit? Equivalent circuit of this particular diode will be like this. Okay. So here you can see that we have some capacitance because of this intrinsic region of the pin diode. And along with that, parallelly, we have a huge resistance. See here, 3 kilo ohm. Okay, 3 kilo ohm resistance will be there. So between your ground to cathode, between your ground to edge of this particular SIR, we have a huge resistance. As there is a huge resistance, obviously signal will not flow through this path. It will go to the output end. Okay, so it will go to the output end because from input to output you have 50 ohm only. But through this path of diode, when the diode is off, it is offering a 3 kilo ohm of resistance. So it will be fully off. It will behave like an open-end resonator. Means the resonance frequency of the SIR3 will not change if the VDC is not applied, or the diode if it is in reverse bias or in off mode. So here I can see that when the VDC I am applying, this first pass band will be stopped. If I am not applying, it will be as it is. It will be intact. Similar, same case will happen with the second SIR4. SIR4, when I am applying VDC, some positive voltage, this particular diode will be turned on because of this low resistance path, and this edge of the SIR will be connected to ground, and the resonance behavior of the SIR4 will change. It will not resonate at 5.35, and 5.35 will collapse simply. Okay, and without the application of VDC, there will be no change on the pass band, right? Okay, so this is how we can see. So these are the transmission line model. I will not discuss this part of it. Okay, so I'll directly come to the see here what we are doing. See, these are the different cases. See, first figure A. Figure A, what we are doing? Both the diode are off, D1 and D2. So D1, D2 when are off, resonance behavior, as I have told, SIR3 and SIR4 will not change. I'll get a dual pass band, right? I'm getting dual pass band. Okay, so it will operate in two bands. Now in case of B, diode 1 is off. So D1 is off, means this is reverse bias, or VDC I am not applying. But D2 is on. D2 is on means VDC I have to apply here. So when D2 is on, this pass band will collapse. 5.35 will collapse. See here, I am not getting 5.35. Okay. So the huge attenuation at 5.35 is close to 20 dB. Okay, 18 or 90 dB around where it is. Okay. So similarly, case C. In case C, what we are doing? We are also doing D1 on. D1 on means the first pass band will collapse and second pass band will not, because D2 is off. So here you can see that second pass band is present, the first pass band is fully collapsed with an attenuation above around 16 dB. Okay, and fourth one, when both are on, see here, when both the diodes are on, then both the pass band will collapse, right? Okay, see the case 4. Both the pass bands are not present here. So what I can see in short, in conclusion,
Excuse
that,
me, sir. Excuse me.
Yes, yes.
Sir, the selectivity of the second pass band,
Ah.
if you see the upper pass band edge of the second pass band, probably there is a deterioration of its performance. The selectivity regarding the second pass band. The first pass band is excellent, but if you see the second pass band upper edge,
Right,
probably.
right.
So what is the reason for that, and how if I try this, how I can do the improvement over this, sir?
You see see this thing, the blue one, maybe you are looking at the blue one. The pink one is basically the circuit simulation, and the EM simulation is the blue dotted line. Okay, so if you look at the blue dotted line for case C, the transmission zeros are fully visible. See here, the transmission zeros are fully.
Okay, sir. Okay, thank you, sir.
Can you hear me?
Yeah, you are audible, sir. Go ahead.
Okay.
Yes,
So fast pass, sorry, this transmission zero is not fully prominent, right? Okay. So this is fully depends on that how the transmission zeros you have placed, right? See, this was placed at 6.3. Now, somehow, if you can place it at 6.1 or 6.2, you'll be getting more selectivity. Okay, see here. So the transmission zero, it is placed near to 6.1 around. If you can place it close to this pass band, maybe at 5.8, okay, your problem may solve, means you will be getting more selective response. Okay. But as I do not have here in this structure, later on I can see something, some new structure where this kind of problem may be solved. But here I do not have a full control over the transmission zero, right? Okay, the transmission zeros are basically placed due to this multi-path propagations. The signal which will be out of phase fully at port number 2, those signal will be blocked, will be stopped, and I'll be getting a transmission zero. Okay. But here, as you cannot change the structure, okay, so you do not have the control. As you are telling that, how can I improve? Okay, but here the chances is less, okay, because you do not have a separate mechanism here to control the 6.3 transmission zero. Okay, is it clear?
okay, sir. Okay, got it, sir.
Okay.
Excellent.
So you have to be happy with this selectivity only. Okay. So later on, I have we have designed some monopole antennas. Okay, so dual band antenna. So we are using triangular patches. Okay, so we have used triangular patch, 2 triangular patches. The resonance frequency you can calculate from this expression, triangular patches. We are using 2 triangular patches of 2 different resonance frequency. And the ground plane we have tapered just to have proper impedance matching with the patches. And this is the what I can say, that S parameter. Okay. So S parameter of the antenna. So first pass band is giving around 7.7%, and second one is around 5.8, which is matching with the required pass band specifications. Okay. Then this we are cascading. Okay. So we are getting a gain of 3.7 dBi for first pass band. For second pass band, we are getting around 5.2. Okay. So then we are cascading this structure together. So we have cascaded this structure together, and we are getting the reconfigurable filtering antenna. So filter and antenna cascaded together, and we are not using separate areas. The same tapered structure below that antenna. On the top of that, we have placed the filter structure and the required diode and other RFC and all. Okay. So this is the fabricated prototype you can see. Okay. Here. So here we have used this black part. You can see this pin diode. Okay, then through this particular path. Okay, one RFC is here. Okay, very small in size. Okay, so through this where we are providing VDC through the RFC, and will come to this diode, and the diode will be forward and reverse bias as per the voltage provided through this wire. Okay, so here we have used one simple RFC SMD type. We are also use another pin diode. Okay, this we have connected. Okay, this after fabrication connection is a very big challenge. So the pad, the line, the pad of the RFC and your diode will be hardly 0.3 or 0.4 mm. Okay, and very small size of pad. How to place over the edges of the SIR is very challenging. Okay, and you have to be very much careful that unnecessary metal you cannot melt, then the entire response will change. Okay, so if it is the frequency is higher and higher, then this problem will be more prominent, right? So this is the measured EM simulator results. Okay, so here you can see the way we have explained the filter the same way the cascading filtering structure is behaving. Okay. So when both the diodes are off, then dual band, then single band, another single band, finally no radiation. Okay. So this is the radiation pattern of the filtering antenna. Okay. So here the gain we are getting around 3.21 dB at 3. After measurement, actually this resonance frequency shifted a little bit. And for 3.25 we are getting 3.22 with a gain of 3.21 dBi. And for the second passband, instead of 5.35, it is showing 5.46. Okay, little shift is there, and the gain is reduced a little bit, 5.08. Okay, and core pole and cross pole means there is higher than 14 dB. Okay, so cross pole and core pole, the separation level we are getting more than 14 dB for first passband. For second passband, we are getting around 17 dB. So this is for different cases. Okay, so this is for when both the diodes are off. Okay, so this is for D1 for case A, when the D1 is off and D2 is on. Okay, when the single passband we have. Then case B, when 5.35 only radiating. Okay, and obviously when the single passbands are radiating, we are getting little more improvement in gain. Okay, and the variations we can see the measured and simulation variation we are getting 0.5 to 0.9. Okay, dB lower always coming within the simulation and the measurement. Okay. So conclusion. So we have for this part only. Okay, so we have designed this dual passbands reconfigured filtering antenna, where the filter is playing the crucial role to decide the resonating frequency of the operating frequency of the antenna. So by suitably choosing the bias voltage to the individual diode, you can switch between different bands, right? Okay. So this dual band, another structure. Okay. So here, instead of discussing full in detail, here we are using. I'll directly go to the structure part. Okay. So here between input and output, here also this dual band. Okay. So in the top side, we have used SIR. Okay, two resonators we are using. So it is second order filter. In bottom side also now you are using UIR, this uniform impedance resonator. Okay, this is SIR, and the bottom side is UIR. Okay, the same way. So our target frequency is 3.2 and 5.5. Only the structure is different. Okay, so here we are using. See here, this will resonate at 3.2. It will couple to this resonator, and again it will come to the output port. And the lower part of the resonators are working at 5.25, so it will couple to the another 5.25, and will come to the output. So order will be second. So between input and output, it is encountering only two resonators for individual bands, top side and bottom side. So top side will be doing at 3.25, bottom side will be working on 5.25. Now when you are going to collapse the operating frequency. So obviously the same pin that I'm using. So you see, suppose this is the resonator. I cut a small part of the resonator. Okay, so I cut a small part of the resonator, and there I have introduced the diode. Okay, so pin diode. Same thing I have done with this also. So I have changed this. So once this is off, see, once this is on, you can say that this particular section to this particular section, this entire section will be connected together. It is connected with a very low impedance path. Okay, so these two sections will be connected together. So entire means resonator will be connected. So its resonating conditions or resonating operations will be preserved. But when the diode is within this top section of the resonator and bottom section of the resonator is connected with high impedance, you can say it is basically open in nature. Then the resonating behavior of this entire resonator will change, and I will not get the passback. Now, when you are introducing the pin diode at the middle, you have some problem with the ground. That how will connect the ground? Okay. Now here also grounding I am doing through RFC. Okay. Initially it was not the case. Okay. See the first structure. First structure, what we did, the cathode I have directly connected to the ground. Okay. I'll make a hole over here or a via, and I can directly connect it to the ground. But in this particular case, as you cannot connect the cathode to ground directly, so you have to provide this. You have to connect through RFC. See here, this is the via. Via means this is ground. So ground will be connected through this RFC. Then it will come to this microstrip line, and it will come to the cathode of the pin diode. Okay, cathode will be connected to the ground. Now I cannot directly connect it to the ground. Then the signal which is passing through this means resonator, that will also be connected to the ground. It will be grounded. So that is the reason we have to connect one RFC. Okay. So as this is RFC, so obviously it will not allow the RF signal to pass through the ground, right? Okay. So RF signal, when it will be coupled from input to the resonator, then although a ground is connected through RFC, but it will not be coupled because your inductor will not allow this RF signal to pass through, right? So it will go to this diode. Okay. But when it will come to the DC, so then this RFC will not create any problem. So we will be directly connected to the cathode of the pin diode. Okay, and when I'll make a forward bias, so obviously again here I have to put one RFC. So it will be forward bias, the diode will be fully means on with the low impedance value, right? Okay, so this is how the arrangement you have to do. If you're connecting a pin diode at the middle, you have to provide a separate ground through RFC, and then for biasing also you have to connect one more RFC, and through which your DC will be connected, right? So in this structure, I have used 1, 2, 3, 4 diodes. And 4 diodes for individual diode, I need 2 RFCs. Okay, so 8 RFCs you have to use. Okay, so this is the structure is okay. So this structure is also operating in 2 bands. Okay, so as you can see that when first pass band, both the pass band you will get. Okay, when both are on, right? When all the diodes are on, D1, D2, D3, D4. When all are on means all are connected together. So all the sections are intact. So I'll be getting 2 pass bands, right? And when the second case, when the D1 and D2 are on, so your D1 and D2 are on means these 2 sections will be connected. Only upper part will generate the pass band. The lower part, as it is disconnected, so these are open. So the resonance behavior of this particular section will be different. So I'll not get the second pass band, right? So only 3.2. Similarly, when this particular D3 and D4 will be on, so then the second pass band I'll get. The first pass band, as these 2 are off, I'll not get the first pass band, right? So 5.5 will be there. When all are off, then all stop. There will be no more radiation. No pass band, no radiation. So this is how you can see. Okay, so the characteristics of for different cases of on and off of diodes. Okay. So finally, I have used a simple patch, rectangular patch with tapered field line. So this is basically giving me a broadband radiation characteristics. So starting from around 2.8 to 6 gigahertz. So this I have to connect it to the filter structure. This is the fabricated prototype of it. Okay. So with the help of proper biasing to the pin diode, we can switch the operation from dual band to single band, again from single to another single band, and no radiation. Means there will be no more pass band provided by the band pass filter. So obviously, the filter antenna is not going to radiate. So switching can be done from dual to single, then single to another single, then also. Okay. So this is the radiation pattern. For gain, we are getting around 4.57 and 5.5 in between. Okay, for these 2 pass bands, and measured cross pole level is below 30 dB. Okay, so this is what we got. Okay, and I'll discuss one more, that is your triple band integrated band pass filter. So not this structure. I'm still have so many slides. Okay, I'll go for only the last part of the structure, that is the fractal triple band reconfigurable. Okay, so I've seen 2 different dual band reconfigurable filter. Only one structure of triple band reconfigurable filtering antenna I'll discuss here. Okay, after that I'll finish my presentation. Okay. So I'll directly move to the structure. So here you can see that this is the structure of the filter. So in this structure, we have used 3 pairs of resonators. Okay, triple band. Okay, so as you can see here, triple band. So here I'm using 3 pairs of resonators. Okay, so in these 3 pairs of resonators, we have 2 SIR. Okay, and 2 pairs are SIR, and 1 is UIR. Okay, so here you can see R1 and R2. So R1 and R2, this R1 and R2 both are identical. Okay, these are operating at These are operating at 2.4, 3.5, and 5.4. Okay. So our resonating frequency are 2.4, then 3.5, and 5.4. So SIR upper and lower half of the feed line operating at 2.4 and 5.4 gigahertz is for Bluetooth and WLAN applications. And a pair of UIR is operating at 3.5, which is basically supporting the WiMAX. Okay. And pin DATs we have used. Okay, see here. So these are the SIR, one SIR, R1, and another is your R2. This we have designed to operate at 2.4, okay, to cater the Bluetooth. Then this UIR, okay. So this at the top of the SIR, we have placed the UIR. Okay, so this UIR we have basically designed at 3.5, sorry, 3.2. And at the bottom side, we have used the SIR again. This is operating at 5.4. Okay. The same way, this coupling, mutual coupling between the resonators, you have to calculate, as I have discussed earlier in the first filter design. Okay, for every cases you have to do. Okay, you have to see that how much will be the coupling length. So if you look at these two SIR, so this particular is the coupling section. So this particular is the coupling section. So this you have to decide that how much will be the coupling section. For second passband, these are the coupling sections. This length you have to decide that how much coupling length I have to provide to achieve the desired fractional bandwidth. So here, this is the separation distance which you have to control. Okay. So with this, I have this is the same process I have explained. Mutual coupling you have to calculate. Okay, for individual bands. Then finally, you'll be getting, see here, the triple pass bands. Okay. So triple pass band we are getting the triple pass band filter. Now additionally, see here with this structure. Okay, so the structure which I have presented here. Okay, so this is providing a response like this. But additionally, we have used this stub. Okay, at the input and output side. With the presence of this stub, one transmission zero is placed between these two pass bands. First and second pass band. See here. Additional transmission zero we have placed. Okay, so this is basically helping to improve the selectivity of the individual bands. Okay, so this transmission zero is due to stub. Open-ended stub we have used. Okay, and this stub is lambda by 4 in length, so lambda by 4 open-ended. Okay, so at 2.75 gigahertz. So this length, if you look at L2 will be lambda by 4 at 2.75. So as it is open-ended, so at 2.75, it looks like a short circuit, and the signal will be shorted, and a transmission zero will be created. Okay. And finally, when you're designing a reconfigurable filter, the same process we have done. The sections of the microstrip for both the resonators I cut, and I have introduced the pin diode. Okay, here also the same thing we have done. Okay, for the second UIR, the first UIR also a part of the UIR we have cut, and the pin diode we have introduced. Here also you can see that you have to provide separately the grounding, right, through RFC. So biasing you have to do through RFC. Again, the cathode will be grounded through the RFC. Okay, so same arrangement we have done with the lower sections of the resonator. Okay, so a part we have cut and introduced the pin diode, and cathode is connected to ground through RFC, and anode I'm connecting via. So these are the different conditions. Okay. So here you can see by suitably choosing or on and by suitably turning on and off the diodes, you can reconfigure the pass band. See here, triple band to dual band, again from dual band to another set of dual band. This is another set of dual band, then a single band, then multi-single band also you can do. Okay, so these results are not here with me, but you can go for multiple single band also. Okay, and finally all stop. Okay. So this is a triple band reconfiguration, which can reconfigure to WiMAX to Wi-Fi. Okay. So this is how we got. Because most of the cases you see when you are designing the reconfigurable filter, as you are placing the pin diodes in between the resonators, right? Okay, you'll be getting more insertion cost. So, but if you are putting at the edge, somehow if you can design a structure which where the pin diode will be placed at the edge, in that case insertion loss will not be that much. But here you'll be getting more insertion losses. Okay. So here, see here, we are getting 2.1 to 2.15 dB around. Okay, this amount of radiation, huge amount of losses we are getting because of this placement of the diodes. A fractal tree we have used to design a multi-band filter. Okay, sorry, multiple antenna. So multiple antenna we have designed to operate at same 2.4, 3.25, and 5.5 gigahertz.
Sir, just I have one query. What kind of fractal it is? What kind of fractal you have shown?
This is fractal tree.
Fractal tree.
Hmm.
Okay. Actually, I think that fractal tree, this type of fractal
No,
can be
this is
any
little
tree type.
modified. This is little modified. Some angle we have modified.
It is modified, right?
It is modified.
Okay. Okay.
So this is maximum peak we are getting up 5.08 dBi. Okay. So finally, these structures we have cascaded together, and we are getting the reconfigurable filtering antenna. Okay, here we can see the measured comparison between the measured and simulated results. So you can see
Sir,
that.
I have one query. Sir, I have one query in your earlier slides. You have seen some kind of fabricated prototype. From where you have done the fabrication? Yeah.
This one.
Yeah.
No, this one is to do from Hyderabad.
Okay. I think that the fabrication is very much accurate. They have done.
Fabrication
go ahead.
is very much accurate, and the main problem is with the placement of those pin diode and RFC.
Diode.
This is the most crucial
Diode
part.
and RFC. Most crucial part.
So you have
Okay,
to go to this, especially those working on repair of mobile. Na? So this mobile
Yeah.
shop. So you have to find some suitable mechanic who can do all those things. So that part
Yeah.
is very important. So means in your lab you cannot place all those components.
Yeah. Okay.
So this is the measured and simulated results. So you can see that how the operating frequency can switch from triple to dual band to single band and all sorts. Okay. So this is the radiation pattern of the combined structure. Okay. So okay, in conclusion, you can say that triple band is also possible to reconfigure between different, we can say triple to dual to single and also stop operations. Okay, these are the references. Thank you. So you have actually.
Okay. So.
Okay. If you have anything to ask, then.
Yeah. So thank you, Dr. Pankaj Sarkar, for your nice presentation. So now I will ask participants to ask any questions if you have. If you have any queries, any doubts regarding filters or related topics, you can ask. Yeah. Is there anyone?
Design process of filters. The first structure I have discussed in detail, that how a filter can be designed and how to get the different transmission zeros and poles. Okay, so that techniques you can use for all the configuration. That's why for other reconfigured filter, I have not discussed in detail the design part. I think the one, so the first one I have discussed in detail. So that same thing you can apply there.
Okay. So I think that, sir, there is no question from any side. So keeping this view, I am ending today's session over here. So thank you once again for your nice presentation.
Thank you, sir, for inviting me.